Hello, so this is group 2 doing a presentation on sensors. This is done by members Michael Schneider, Natasha Zabib, Nicholas Wiest, and James McDonald. So this presentation will essentially go over what kind of sensors there are and how they can be applied within the real world and why they are important in our everyday lives. So we will begin this presentation with Michael Schneider giving an overview on sensors and how they can help us in our everyday lives.
So let's start with what is a sensor. A sensor is defined as a device that responds to a physical stimulus and transmits a resulting impulse. Meaning, if you want to get information from one end of your analog to another, you need a sensor in order to interpret that information and compile it into the microcontroller. So sensors are a abundant resource that we use in everything. We use an accelerometer in our phones. We even use GPS sensors for location in our phones. VR headsets also have IMUs, so accelerometers, gyrometers, and everything like that to make sure and to track it in physical space. It also has cameras on it, which are another form of sensor, light sensor, in order to properly track where the VR headset is in 3D space. And when combined with other sensors, engineers are able to create insane complex machines. One example of this is in California Adventure in Disneyland. There is a Stuntronic, which is a humanoid figure that Disney has created to mimic Spider-Man. It acts like a normal human would. It has the typical humanoid autonomy, but it is equipped with IMUs and accelerometers so that it can do flips in the air like Spider-Man and web swing from building to building, and it can actually detect how many flips it's done, how close it is to the ground, so that it lands on its feet every single time. So why are sensors so important to engineering design and practice? Sensors are the building block of engineering. You can wire something, but it needs to get to a sensor if you need the subsystem to actually complete a task, especially if that task requires user input. With user input, everything has to go through a sensor. If you have a keypad, the keypad acts as the sensor. For example, if there is an automated blind system that uses the threshold of light in the room to adjust the blinds, it doesn't work unless you have a light sensor that is able to take all the information of the ambient light in the room and with software and proper wiring, adjust the blinds accordingly. Sensors allow for high efficiency machines in engineering applications. By designing efficient sensor use in systems, engineers can redefine aspects of life. And one of the great things about engineering is that you're always building upon other people's designs and you're always trying to improve quality of life. Sensors are a great way to do that.
Thank you, Michael. I'll take it away from here. We'll give a couple of examples of active and passive sensors, but before we do that, let's touch on what active and passive sensing actually means. Well, a passive sensor is a device that detects and then responds to some type of input from the environment. Typically, passive sensors, they gather data through the detection of vibration, light, radiation, or just really any other phenomena occurring around the sensor's environment. And in a passive sensor, the output power is almost entirely provided by the measured signal without an excitation voltage or an external source of power. Meanwhile, an active sensor, they require that external source of power. And that source of power provides the majority of the output power of the signal. My colleagues will touch on a few active sensors, and I'll describe a couple passive sensors. And to touch on what Michael was saying a little bit earlier ago about those specialty blinds, we'll touch on the LDR, or the light-dependent resistor. And we'll also touch on the PIR, the passive infrared sensor, which we see in most high-end homes, classrooms, office spaces for occupancy detection and light detection. As I was just saying, here's a good example of an LDR. As we can see, the LDR is a type of variable resistor, which almost like a potentiometer, but without a little knob to turn. What happens is that little groove that you can see, photons bang into that, and depending on the amount of photons that are hitting that little groove, the resistance of the LDR increases or decreases with the intensity of the light, aka the amount of photons hitting it. As you can see from our little graph down here, the resistance of the LDR is inversely proportional to how many photons are slapping into it. So this makes it a very useful tool for many light detection applications. Here's another example of an LDR, again very similar to the first one shown. And the beauty of this is you can see it's very small, it's very easy to produce, there's not many components to it, which makes it incredibly useful for all applications that involve light detection. The amount of applications that involve light detection is honestly staggering. Just a couple of examples are from the high end of LDRs are used in infrared astronomy to something as simple as they're used in a lot of security systems, or they're used in traffic cameras, they're used in street light controls, even down to your cell phone when you're on it and it adjusts the brightness of the screen depending on how bright the sun is behind you or the room that you're in. LDRs are virtually everywhere where there's a sensor and there's light. Next on our list of passive sensors, we have the passive infrared sensor, or the PIR. This is slightly more complex than our LDR, which we just talked about, but not by much. This is a very widely used sensor, and it works off of a very simple principle, which is that everything in the universe, whether it be a rock, a person, a planet, a star, all gives off some level of infrared radiation. And by using a PIR, it can have that infrared radiation enter into the sensor, and then we can do various tasks with that information. For example, a NASA space telescope can determine movements of planets and stars and wobbles based off of infrared information that's coming into the sensor. Or you can have something as simple as the automated doors when you walk into a hotel lobby that notice when you step in front of them. The idea is that you can fine-tune your task based off of the wavelengths of the infrared radiation entering into your sensor. Now on this slide, we'll quickly touch on the application of motion detection using a PIR. As you can see, the average human body, or mammal, gives off a temperature of about 93 degrees Fahrenheit. That temperature correlates to between 9 and 10 micrometers of wavelength in infrared energy. So the sensors for motion detection are typically set between 8 to 12 micrometers, give themselves a little bit of play, in case it's really cold out, really hot out, etc. And using this information, they can then use them to set off that alarm system, to open that door. Obviously, as the infrared radiation increases or decreases, you'll be able to change your application as needed. Now, that was just a couple of passive sensors, very common ones that we see all the time. My colleagues now, Natasha and James, they'll follow up and they'll give some examples of some more active sensors, some sensors that require some power sources to be brought to them and that have a little bit more of a wider berth of capabilities.
All right, so to give an example of an active sensor, to continue on what Nicholas was talking about, I'm going to be discussing about an accelerometer. So as we know from physics that the acceleration is the velocity divided by time. So this sensor measures the acceleration of an object. The sensor is operated based on the measured acceleration, of course, and since this is an active sensor, it is essential that it is connected to an external voltage source. So as you can see in the picture on the left, there's the 5 volts or the 3 volts pin that you can choose from when you're doing a project. So let's discuss the function of an accelerometer. So of course it detects the acceleration, but it utilizes an XYZ axis diagram as I show on the right of the picture. So it can detect movement from the x-axis or the y-axis or the z-axis. So another example of an active sensor is the initial measurement unit, or IMU for short. Sensor measures the rotational rate. So this sensor is pretty interesting because it actually combines two different sensors, the gyroscope and the accelerometer. So the accelerometer I just went over is the sensor that measures the acceleration of an object, whereas the gyroscope is a sensor that measures the angular velocity of an object. So it also has the 3 axes as well, but instead of measuring the acceleration, it just measures the angular velocity. So this sensor essentially just combines the two of them. So now for more information on that, so let's talk about the function of an EMU sensor. So as I mentioned, this sensor also has the 3-axis diagram, but instead of us just calling it X, Y, and Z, there are different terms for them. So there is the pitch, which is considered the x-axis in the case of the accelerometer or gyroscope. There's also the roll, which is considered the y-axis in the case of the accelerometer or gyroscope. Lastly, there is the yaw, which is considered the z-axis of the accelerometer or the gyroscope. So this sensor, the EMU sensor, can be used in an aerial vehicle, a ship, or a submarine, or any other form of transportation that requires the understanding or needing to know what is going on angular-wise, like the velocity. Whereas the accelerometer can just kind of be used in a car where it's just only going one direction, one speed, and not really needing to worry about the angular motion of the environment around this car. So we gave a few examples on passive sensors and active sensors. So let's talk about the applications of an active and passive sensor in the real world. So let's start with the passive sensor. So in this example, I'm going to be talking about a camera. So let's imagine that we want to take a picture with a camera on a sunny day, right? So there's no clouds in the sky, it's very bright outside, and we just want to take a picture. So keep in mind the day is sunny, so there's no need for a camera flash. So since there's enough light directed towards the lens, the camera can just take in all the radiation that's being provided around it within the sensors inside the lens. So there's no need for us to put any external source of light or to turn on the flash on the camera. So an example of an active sensor is a police radar detector. So this one, it depends on the time of day, the car speed, what kind of car it is, what the pulses are that the radar is detecting. So this sensor is based on a lot of external voltage sources or any sources in general in order for it to operate. So that is said for the applications that these sensors can be utilized. We basically discussed that the use of sensors can actually be very essential for our lives, and they can make our lives a lot more efficient and easier. However, there are some ethical and controversial opinions and topics on sensors, such as privacy aspects in regards to the sensors collecting some of our personal and or private data. So the sensors can actually be used within our healthcare on patient data, within our homes as well, when we have our, for example, Amazon, our Alexas that know our music tastes, our playlists, where we shop and what we shop for patient care within healthcare aspects where they know our addresses, our disease, like any diseases we may have or any health complications, and our medical history, which is some information that some people may not want others to know and just keep private for themselves. These sensors could collect the data, and a lot of these sensors are being sold by a lot of big manufacturing companies, well-known companies too, such as Amazon, like I talked about earlier, and a lot of hospitals and hospital devices, maybe like Johnson & Johnson. So these sensors collect a lot of data that can be considered private and personal for someone, and it's a little bit of a controversial topic since those sensors actually collect more personal data rather than data that can, be known by other people. So that is something that people do mention a lot as well.
Okay, so we're going to talk a little bit about coding examples in regards to the sensors. So this first example here we have is the LDR sensor, and this is using the Arduino. And this specific one, this is C, but I converted to C++ just because it was giving me some errors. So still works same way on the Arduino. Yeah, so what's happening here is, so it's going to check to see if it is dark, and then it's going to turn the LED on. And then if it's not dark, then it's going to turn the LED off. And you can see there, it says serial.print. It's going to print what is in those quotes. So it's dark, turn the LED on, and then it will also print the status. And then in the else statement, it does serial.print. It is too bright. Turn off the LED, and then it'll also print the status again. And then at the top there, the void setup, that is just kind of going through the pins and what you need to use there with output and input. All right, so we're going to continue on with coding examples. In this one, we're going to talk about the ultrasonic sensor. But first, I'm going to explain what an ultrasonic sensor is and how it works. So an ultrasonic sensor works by sending out a pulse of ultrasonic sound, and it listens for an echo. When that pulse of sound hits something, it's going to cause an echo, come back, and the sensor is going to pick that up. So to use this is any form of measurement. You can take the duration that the duration in seconds that the pulse takes to go from initial pulse, like form, to the to hit something and come back. So that full loop. And then you'd use the speed of sound to determine the distance. So with this specific sensor, it's a pretty, decent one from what I've read. I guess they use temperature correction stuff, which makes this device unique. I guess it gives more accurate results. Anyways, so we're going to talk about the code here. So we'll start from the top, obviously. So first we have to define a few things. So we have some integers here. First one is a representation for 1 centimeter. And then we have the trigger pin, and we have sensor pin, sensor value, which are just kind of initial values. And then we're going to go into setup. So that kind of gets everything going here. Serial begin kind of starts the sensor, and then it's going to go to pin mode, and then we're going to set the digital write to high, and we're going to set another pin mode to input. And we're going to delay 500 here, just kind of initialize the sensor, and then we're going to get an output once that is good to go. It's going to continue either way. And then next we're going to go into this loop. So we're going to delay a little bit here. And so then the sensor is going to start reading. And that means that the pulse, well, it's going to start reading and listening. So that means that the pulse has been sent out at this time. It's going to wait for an echo. So if it's too long, then invalid, because the sensor can only measure a certain distance away. If the echo comes back, the distance is measured by taking the time and dividing it by 50, which is 1 centimeter. And then if not, then we're going to just get a sensor value here at the end. And this would kind of be the output right here in the middle of the screen. It would just keep looping and looping and looping until you tell it to stop. But it would just keep looping. It doesn't really show any difference in distance, but obviously it would change if you did move it. So yeah. All right, so we saw C, we saw C++ in the last two. So we're going to show you a Python one for the last example, and we're going to use a LiDAR sensor. So yeah, this is in Python, a little bit easier to read. So yeah, so we're going to start from the top, kind of just the configuration right there. We're going to move down to the output. So it's going to grab all the data from the scan, from the LiDAR, from the configuration that has been chosen above, and it's going to append this all to an array for the distance, and we're also going to have a time array, and then it's going to print all these values out on screen for you. And at the bottom there was a matplotlib, plot chart that it would print out for. So yeah.
So now that we had done the presentation on sensors, types of sensors, and how they can be applied in the real world, here are some 5 questions for you all in the audience to answer. So what is the definition of a sensor? What is the difference between active and passive sensing? Why are both active and passive sensing needed? What are more examples of passive and active sensors? And lastly, what kind of projects can be made with the sensors mentioned within this presentation? For those of you who are interested on this topic and want more information on sensors, feel free to use the link below or to just look up tech exploration and look up sensors introductions. They give a lot of more information on the sensors in this presentation, and as well as different sensors and example projects that you can use to practice along to better understand these sensors as well.